Today we're taking a look at complex numbers. Now, before we jump into our notes, it's important to understand what complex numbers are. Earlier on this year, we took a look at the number sets and we studied real numbers, for example, and we said real numbers can be broken up into two categories. Irrational numbers, those numbers that cannot be written as a fraction of integers, and irrational numbers, which can be written as a fraction of integers. And then we said underneath the rational numbers, you had integers, which are both your positive and negative whole numbers. And then you had whole numbers, which included 0 and counted up from there, 1, 2, 3, 4. And then you had natural numbers, which were your counting numbers, 1, 2, 3, 4, etc. Well, if we take a step back beyond real numbers, we see that we actually have complex numbers, and that all numbers are actually complex numbers. Complex numbers consist of this form of a real part plus an imaginary part. So let's jump into our notes today and take a deeper look at those complex numbers. A complex number takes on this form a plus bi, where a and b are real numbers and I represents the square root of -1. So take this complex number, for example, 8.6 plus 3i. 8.6 represents the real part. In other words, a, this number that stands alone, represents the real part of that complex number, and 3 represents the imaginary part. Now, it's important to note that it's not 3i. I represents the square root of -1. It's just 3 that represents that imaginary part. So let's take a look at a few examples, and what we're doing here is we're simply adding and subtracting complex numbers. Now, the way you can think about this is think of that imaginary part like a variable x. We would add and subtract like terms. So we're going to add and subtract our real parts, and we're going to add and subtract our imaginary parts. So I see I have a positive 6 plus 3. That results in a real part of 9. And I have a negative 5i plus a positive 4i. When I combine a negative 5i and a positive 4i, I'm going to end up with a negative 1i. So adding these two complex numbers results in 9 minus I. Let's take a look at this next example. We have 2 plus I minus 7 minus 2i. Now again, you have to be careful with this minus between these two complex numbers. It really means you need to distribute that minus to both of those terms inside. So I have a 2 minus 7, that's going to give me a negative 5 for my real part. And then I have an I minus a negative 2i, so that's going to act as adding a positive, and that results in positive 3i. All right. Further on, we have a few more examples here of doing some operations with complex numbers. Here you see that we're multiplying 3i, this complex number, times another complex number, 12 minus 3i. Here we're simply going to distribute. So the distributive property will follow like this. We take 3i and multiply it to our 12. That results in 3 times 12, which is 36i. So again, you can see here that I acts very much like a variable x. Next, we have 3i times a negative 3i. Well, a positive times a negative gives us a negative 9, and I times I results in I squared. Now, this should kind of turn a little light bulb on for you. Remember, a few chapters ago, we learned that I squared is equal to -1. So we can simplify this complex number. This is 36i minus 9 times a -1. So a negative 9 times a -1 results in a positive 9. So this is really 36i plus 9. Now, we should write this in standard form for a complex number, which means we'll write the real number part first and then the imaginary part. So 9 plus 36i is a result of multiplying 3i to the complex number 12 minus 3i. All right, let's take a look at our next example here. 4. We see that we have 5 plus 9i times 2 minus 7i. We're multiplying these two complex numbers. And again, we're going to follow kind of that similar pattern of distribution. So we're going to multiply the 5 to both the 2 and to the negative 7i. That gives us 10 minus 35i. And then we're going to multiply the 9i to both the 2 and the negative 7i. That gives us a positive 18i and a negative 63, and then it becomes I times I, which is I squared. All right, now let's simplify by combining some like terms here. I have a positive 10 and a negative 35i, and a positive 18 is going to result in negative 17i. And then I need to take this I squared and change that to a -1. So this is really -63 times a -1, which would turn this into a +63. So that becomes 10 plus 63 minus 17i. So the resulting complex number here would be 73 minus 17i. And there's your final answer for the multiplication of these two complex numbers. All right, in example 5, now we're asked to divide these two complex numbers. We have 5 plus 3i divided by 2 plus I. And we want to rewrite this in a plus bi form. In other words, we need to get the complex number out of the denominator. Well, in order to do this, we need to multiply by the complex conjugate of the denominator. So the complex conjugate of 2 plus I is 2 minus I. Now remember, the complex conjugate is formed simply by writing the opposite value of that imaginary part. Now, in order to get that out, we're going to multiply both the top and the bottom of this fraction by that complex conjugate, because in order to keep it equivalent fractions, you have to multiply the top and the bottom by the same thing. So here we go. We have 5 plus 3i divided by 2 plus I. And we are now going to multiply straight across. Now, when we multiply straight across, again, we're going to do that distribution property. So 2 times 5, which is 10, and a 2 times a positive 3 is plus 6i. Now we have a negative I times that 5, so that's negative 5i. And a negative I times a positive 3 is negative 3i squared. All right, all divided by, now on the bottom, we're going to have 2 times 2, which is 4. And then a 2 times a positive I, which is a positive 2i, and a negative I times a 2, which is negative 2i, and then a negative I times a positive I, which is negative I squared. Now an interesting thing happens here in our denominator. We have a positive 2i and a negative 2i that will cancel those imaginary terms out. This negative I squared, remember, is really negative 1. So what we have in the denominator is 4 minus a negative 1, which turns that into adding a 1. And so our denominator simplifies to just a real number, 5. Now let's simplify our numerator. We're going to combine the 6i and the negative 5i to give us positive 1i. And I'm going to write that in the imaginary part. Now, I'm also got to combine my last term here, which is negative 3 times a negative 1. So that turns out to be a positive 3 plus 10. So 10 and 3 gives me 13. All right, so here I have 13 plus 1i over 5. And this solution now becomes 13 over 5 plus 1/5 I. And now this is written in complex form where you have a plus bi. All right, let's try one more of these examples here. We have 2 plus I divided by 3 minus I, and we want to rewrite this in a plus bi form. In other words, we need to get that complex number out of the denominator by multiplying by its complex conjugate. So I'm going to write 3 plus I on the top and the bottom here. And I'm going to multiply that to the fraction that I have. Okay, when we multiply fractions, we multiply straight across. So this becomes 3 times 2, which is 6. 3 times I, which is a positive 3i. I times 2, which is a positive 2i. And then I times I, which is a positive I squared. All right, all divided by, now we have 3 times 3, which is 9, positive 3i, a negative 3i, and then finally a negative I squared. Okay, again, what's going to happen in our denominator is that these imaginary terms are going to cancel each other out. This negative I squared, remember, is negative 1, so that becomes 9 minus a negative 1, which is plus 1. So my denominator is 10. And now let's simplify our numerator. I have a 3i and a 2i. That simplifies to 5i. And I have a positive I squared, which remember is negative 1. So this is 6 minus 1, which is 5. So I have this 5 plus 5i divided by 10. And that can be simplified to the complex number of 1/2 plus 1/2 I. And there you go. You've simplified that into a complex form.